everyone. Welcome back to the session on machine learning for cancer detection, part 3. Yes. So previously we have covered the following part like foundation, in that we have covered what cancer is, why early detection matters, and quick overview of three focus cancers. Yes. And in part 2 we covered about data and its pre-processing. And then we covered part three, which was all about supervised learning algorithms. And we covered part four, that was all about deep learning and cancer specific models, including image based analysis. So now let's start with part five. Yes? Yes, so this is our part five, that is evaluation and explainability. But before diving deeper into evaluation and explainability, Let's let's just have a demo on how skin cancer model works and how blood cancer model works. So let's have a demo of it on Colab. So let's switch to Colab. And yes, I have run all the commands and I have trained the model before because it takes time to train the model. So let's just switch to Colab and let's understand each and every cell. Okay, and let's walk through it. Yeah, so let's go block by block. Uh, so here in this block, I have imported the data set for leukemia detection using CNN model. So here the statement import Kaggle Hub is used. Kaggle Hub is a small library from Kaggle that lets you download dataset directly inside a Python script or notebook without manually visiting the website. Okay, so this block downloads and automatically unzips the specific Kaggle dataset. And it identifies whose dataset it is and its name, and then it returns a string giving the local folder location where the expected file now live. Yes, so you can see that in output the path is also given, and then we move further. Block 2, it imports Python built-in OS module for working with files or folders, and then it saves path under a clear name, that is raw directory. You can see RAWDIR, that is raw directory. Just remaining for readability in just renaming it for readability in the code that follows. Yeah. Then it is followed by the code def show tree. And so this part of the code defines a show tree function that will recursively print folders contents, and max depth is equal to 3, that caps how many levels deep it will explore, so it doesn't dive infinitely into subfolders. And here depth 0 tracks how deep the current call is. If it's gone deeper than max depth, it returns immediately, stopping further recursion. Yes. Now further, let's come to this part. Okay. Here, os.list directory lists everything files and folders directly inside a root, and then alphabet, and then this here you can see sorted. It's just alphabetize that list for a clean, consistent print order, and guards against calling os.list directory on something that's actually a file, not a folder. If that happens, it just quietly stops instead of crashing. And then let's come to the for loop. and if else statements. Here, entries 15 only look at the first 15 items in the folder to keep the printed output manageable. This dataset has thousands of images per folder. So without this cap, the output would be enormous. And yes, now this line C, you can see if full equals to os.path.join uh, builds the complete path to the specific item, and the print line indents by depth levels, that is two spaces each, to visually show folder nesting. And here you can see os.path isdir. It checks whether this item is itself a folder. If so, then show tree calls itself depth plus one, recursively exploring one level deeper. This self calling pattern is what makes it work the whole nested structure. Here, this line prints the header line showing which folder is about to be explored, then kicks off the recursive walk from the top, right? Now you can see the output over here. This confirms what we predicted earlier, that everything sits inside one wrapper folder, that is CNMC. You can see that. Inside it, the checksum file CNMC leukemia.sums, two unlabeled test folders, that is, yes, flat.bmp files, no subfolders, confirming they can't be used for supervised training, and CNMC training data, which is exactly three folds. It's split into all, that is leukemia, and hem, that is healthy subfolders. The labeled data we need. Now let's move to the next block. Here, this block builds the full path by joining three pieces together with correct slashes, that is producing something like you can see uh, NMC 2019 data set and all, like they are producing a directory. And this is covered path we worked out from our block 2 output. Yes. So here you can see class map is used. It is a directory, it's a dictionary translating the data set's own folder names, that is all hem, into the class names our model will actually use, all normal. This relabeling makes the folder names human readable and consistent with the rest of the course materials. Okay, so now let's move to the next block. So this is our next block where shuttle is a module for copying files, and random is used to shuffle images before splitting, and random.seed42 means makes the shuffling reproducible. Sample split every time you rerun this. Yes, here you can see target directory. This is where the recognized data will live, matching exactly what our main notebook, that is our blood cancer collab file, expects to find. And here val fraction equals to 0.15, that is 15% of each class images will be set aside as validation data. The remaining 85% becomes the training data. Now let's come to our for loop, a nested loop that creates all four needed destination folders upfront. Okay. And it prevents an error if the folder already exists. Example, if you rerun this cell. Okay. Now Let's move further to our file counter block. So file counter will tell you how many images get copied in total just for a final summary print, and loops through everything inside CNMC training data, which we now know is fold 0, fold 1 and fold 2, one at a time. Yes. And here this statement, if not os.path, it skips anything that isn't actually a folder. That is a safety check in case stray files exit at this level. Okay, so continuing further, for each fold loops through both class mappings, building the path to that class subfolder inside this fold and keeps if it is doesn't exist. Next is images equals to os dot list directories. This lists every image file name inside this folder plus class folder. And here random dot shuffle images randomly reorders that list in place. And so the split isn't biased by however the files happen to be originally sorted. Yes. For example, you can say it may be by file name or date. And here well is calculates how many images, that is 15% of this folder should be going for validation and rounding down to whole number. Okay, and well images equals to set images takes the first and well images from the now shuffled list as the validation set and stores them in a set rather than a list, because checking is the final name in the set and is much faster than checking a list, which matters when doing this check thousands of times in the next loop. Okay, now let's move further. So here's again a for loop. Okay, so here loops through every image in this folder plus class folder, and split equals to well. It decides per image whether it belongs to validation if it was one of the randomly selected 15% of training. Okay, here you can see SRC equal SRC where the image currently is. Okay, and DST, that is where it should be copied to. Okay, let's move further. Here F fold equals to this line. Yes, renames the file by prefixing it with its fold name for and okay, so that collisions can be prevented. Since fold 0, fold 1 and fold 2 could each contain a file with the same original name. And here shuttle.copy actually copies the file, that is the original inside the Kaggle hub cache is untouched, and file counter plus equal to 1 increments the running total. And further, it prints a summary that is total images copied. Then for each of the four destinations folders, counts how many files ended up there. So this is the output you can see. So here you can see 10,661 total images were successfully copied and reorganized. And in training, 6,183 leukemia images and 2,882 normal images, that is about 68% and 32% split. Leukemia cases outnumber normal ones in this data set. And important thing to notice is since it's a form of class imbalance, in validation, 1089 leukemia and 507 normal images. Yes. So ratio can be 68.2%, confirming the 15% validation split preserve the same class ratio in both sets exactly as intended. Yes. Yeah, so let's move to the next block. It's about setup and synthetic fallback. So we have trained it on a real data set that exists on Kaggle. So let's move. Here we have used TensorFlow. It is a deep learning framework itself. And here you can see layers and models. Here, Keras submodules for building the CNN architecture, and layers for individual network layers, and models for combining them into a full model. Okay. And here we have used PIL, that is Python Imaging Library, used only for like synthetic fallback, that is drawing fake colored blobs. And it is not required if we have the real original data set, but if we don't have real original data set, then it is required. Here we do have our original data set. As you can see, we have loaded it over here. Yes. So yes, we have written synthetic demo equals to false because we do have our data set. But if we don't have data set, then you can set this true. Okay. So since it is false, so there are no fake placeholder images, and this data directly equals to data blood matches exactly where block 4 put the recognized image, reorganized images. And every image gets resized to 128 into 128 pixels before entering the model. That is, real microscopy images vary in size. The model needs a fixed input size. Okay. And batch size equals to 32. It means the model looks at 32 images at a time during training rather than one at a time, and hence it is much faster, or all at once would use too much memory. Okay. And here epochs are 15, so model will pass over the entire training set 15 times. Yes. So here this defines the fallback function, that is draw random colored blobs as fake cell images. But if synthetic demo, yes, here you can see check means it only actually runs if synthetic demo is true. Since we have set it false, this entire block is defined but never executed. Okay, getting? So this block is never executed, and it can be executed if we set this true. Okay, now loading and pre-processing real images. Keras utility that automatically scans a folder treats each subfolder name as a class label and loads all the images, resizes them to image size, and groups them into batches, that is batch size. And this is why our folder structure, all normal subfolders, mattered so much. Kera infers the labels directly from folder names. Okay. And here you can see label mode equals to binary. Since there are exactly two classes, labels come out as single 0 and 1 values rather than one hot encoded vectors. Yeah. Here you can see label mode binary. Shuffle equals to true, seed equals to 42. Since there are exactly two classes, um, random shuffles images order each epoch helps the model generalize instead of memorizing order and reproducibly. And validation data order doesn't need shuffling since it's only user used for evaluation and not for learning. Yeah, let's move further. That is class names equals to ds dot class names. Retrieves the label names Keras inferred from folder names and in alphabetical order. Printed to confirm they are what we expect. So here you can see layers dot rescaling. It is a layer that divides every pixel value by 255. That is, raw images have pixel values from 0 to 255. Dividing brings them into the 0 to 1 range, which neural networks train on much more stably. Yes, stably. Now, next, you can see over here augmentation. That is a small pipeline of random transformations applied only during training. That is flipping the image horizontally or vertically, rotating it up to 15%, zooming up to 10%. You can see that rotating 0.15, 0.1. So this artificially creates more visual variety from the same images, helping the model generalize rather than memorize exact orientations. Yes, let's move further. Here, preprocess is a helper function, that is, it applies normalization to every batch of images, that is X, while leaving labels Y untouched. And only if training equals to true also applies augmentation. Here you can see dot prefetch tf dot data auto tune. It is a performance optimization. It prepares the next batch of data on the CPU while the current batch is still training on the GPU. So the GPU never sits idle waiting for data. Okay. And this last two lines actually run this pre-processing. Training data gets both normalization and augmentation, and validation data gets only normalization. So this is our output. It confirms Keras successfully found 9,065 training images and 1,596 validation images. These numbers are slightly lower than block 4, which we have seen above. That was, yes. And let's move further. Yeah, here you can also see they're grouped into exactly the two classes we expected. Yes, all and normal. So now next is building the CNN architecture. Here you can see we have used the word sequential, and inside that we have layer input, layer quantity, all these things. So it builds a model as a simple straight back of layers, s- each one feeding into the next. So it builds a stack. Okay. Now here you can see, yeah, so here you can see input shape equals to image size, comma 3. It declares the expected input shape, that is 128, comma 128, comma 3. That is 128 pixels tall, 128 wide, and three color channels, red, green, and blue. The image size unpacks the tuple 128, comma 128 into two separate values. Now, let's see further. Here, three times it is repeated. Conv 2D. Okay. So, a convolution layer that scans the image with 32 different 3 by 3 pixel filters, each learning to detect a different simple visual pattern, that is edges, textures, activation function is ReLU and adds non-linearity after each filter, uh, and padding equals to same keeps the output the same width or height as the input rather than shrinking it. Yes. And here Max pooling 2D is used. It downsamples the image by taking the maximum value in small regions, having the width and height. This reduces computation and helps the network focus on the strongest signals rather than exact pixel positions. And the filter count increases each block, that is 32 to 64 and then to 128, and a standard design. And early layers learn simple, low level patterns with fewer filters. Deeper layers learn more complex, abstract patterns. Yes, let's move further. Now, here you can see we have used global average pooling 2D that collapses the entire remaining image grid. However, large is still is after 3 rounds of pooling and down into a single number per filter, producing one flat list of values regardless of the original image size. This replaces folder and flattens everything and approaches and uses far fewer parameters. Then here we have used dense 128 activation equals to ReLU, that it is a fully connected layer of 128 neurons combining everything learned so far into a higher level reasoning. This is the ANN part sitting on the top of the CNN part. Okay. Then dropout is zero point 0.4. That is during training, randomly turns off 40% of these neurons on each pass. This forces the network not to over rely on any single neuron, reducing overfitting. Then comes dense one, activation is sigmoid. So here we have used sigmoid activation function. That is the final output layer. One neuron squashed through a sigmoid into a 0 to 1 probability, exactly like logistic regression's output. The yes. Now let's move further. Here, dot compile configures how the model will learn, and here you can see Adam 1E minus 3. It is the optimization algorithm with a learning rate of 0.001. That is how big a step it takes when adjusting weights after each mistake. Yes. And then here you can see loss equals to binary cross entropy is the standard error measurement formula for two class problems. That is, it's what the optimizer tries to minimize. Then comes metrics, this bracket, that is your accuracy, ROC, AUC, and recall will all be tracked and printed during the training. Recall is the cutoff, yes, but it's tracking the same catch every real leukemia case. And dot summary prints a table describing the model's architecture. Yes, so you can see the output over here. Now, from top to bottom, we can see the image size is shrinking. Yes, can you see that? 128 into 128, then 64 into 64, then 32 into 32, then 16 into 16. While gaining depth, 32, 64, and 128 channels. So these are the channels. Okay. Now, as it passes through the network, exactly the hierarchy building process described on your image based cancer analysis. Yeah. Here you can see the parameters, that is how many learnable numbers, that is weights, each layer contains, and max pooling 2D and dropout have 0 because they don't learn anything. They just transform data mechanically. The total is, you can see 109889 learnable parameters is the entire knowledge the network will tune during training, and trainable params equals to the total, confirming nothing is frozen. Yes. Now let's move further. It is of it's training the model. So here it watches the validation AUC after every epoch. If it doesn't improve for like 4 consecutive epochs, training stops automatically even before reaching all 15 epochs and preventing wasted time and overfitting. Here, mode equals to max clarifies we want AUC to go up, not down. And here you can see model checkpoint, blood cancer CNN dot keras, monitor well AUC and all. So it saves a copy of the model to disk every time validation AUC hits a new best score. So you always retain the best performing version, even if later epochs get worse. Yes. Model.fit, it actually runs training, shows the model trains, and it repeatedly checks against well DS after each epoch for us for up to 15 epochs, uh, applying both callbacks along the way. The returned history object stores every epoch's matrix for later callback. Now here you can see we have run it for 15 epochs, and always go to your runtime, then change runtime to TP4 GPU, sorry, T4 GPU. It would be on CPU, but you have to change it to T4 GPU. Otherwise, it will take much of your time for running the epochs. Okay. So, yes, here we can see we have run 15 epochs. Yes, you can see your accuracy, AUC, loss, recall, well accuracy, AUC, loss, recall. Okay. So with 9,065 training images at batch size 32, that is 9065 divided by 32, which is almost equal to 284 batches per epoch. And the progress bar fills as all 284 are processed. And yes, so here you can see a trend like, see, accuracy climbs steadily. It is increasing. See here 0.6895, here 0.8099. And AUC climbs from 0.7222 to 0.832. The model is visibly learning and epoch by epoch, and exactly the kind of live progress worth narrating during a demo. Yeah. So now let's just plot the graphs. So here looking at the loss chart, we can see at the left the orange one as well. Line is noticeably jumpy. That is, it is spiking up and down between roughly 0.44 to 0.60. And while the blue line, that is the training line, it is steadily decreasing and smooths out. Yes. And looking at the ROC AUC, both lines trend upward together with validation AUC, that is orange actually sitting above training AUC, that is the blue line, and for most of training ending around 0.87 to 0.88 for validation versus about 0.83 for training. So this is a bit unusual. Validation outperforming training and can happen when dropout or augmentation make training harder than evaluation. Yes. Now let's move further. It is evaluate and save. In this, dot evaluate, this line runs the finished model over the entire validation set one final time, returning all tracked metrics, that is loss, accuracy, AUC, recall, and as a labeled dictionary rather than a plain list. And the reminder print statement reinforces the course's core message about medical model evaluation. That is, and yes, model.save writes the complete trained model to a single .keras file, so it can be reloaded after without retraining from scratch. Okay, so the output shows us that with 1596 validation images at batch size 32, that is 1596 divided by 32, it is approximately equal to 50 batches, confirms the full validation set was processed in just 1 second, much faster than training. And since no learning or backpropagation happens during evaluation, and final validation accuracy is 82.77%, and final validation AUC is 0.8729. Okay, so now this is complete all about what we are talking about blood cancer. That is, we have particularly done this for leukemia. Now let's move to skin cancer. Okay, let's start with skin cancer. So this is the collab I have file which I have already run on skin cancer. You can see over here. The process is just same as we have done for our blood cancer. First, we downloaded the data from Kaggle. Yes, so the process is same. So as we fetch the data and store it locally on our device, the same way we have done in this skin cancer detection model also. Now, so this part is same only. Okay. So this is the output where you can see the data, fetched data. Now let's go to our second block. Yes. Yeah. So here you can see here capital H is used and here small h is used. It means so there are two folders in this in the data set. Okay. So now let's do path setup and diagnosis mapping in this step. So here, this line, your meta CSV equals to OS dot path. It builds the full paths to the metadata file and the two capitalized image folders confirmed correct by block 2 stream. And then next is DXT to class. The here the dictionary translating each of seven medical diagnosis code into our simplified binary label as explained in the components like melanoma, basal cell carcinoma, and actinic keratosis, that is, you can say precancerous, count as malignant, and you can see other also like melanocytic nevi, that is common mode. And these are all four types of benign keratosis, dermatofibroma, vascular lesion, and all. Yes. So here I have defined like what I have used for the, okay. Now let's move further. That is reading the metadata and building a lookup, label lookup. Okay. So here CSV.dict reader reads the CSV, so each row can be accessed by column name like row image ID, that is this what I have written over here, instead by any numeric position. And for every row, it looks up the diagnosis code DX in our mapping dictionary. Yes. Now here you can see dx to class dot get dx returns none if the code isn't in our dictionary. Okay. And here, if statement is used, it only stores the image if a valid mapping was found. Building image to class as a dictionary, ISIC code, benefit. Yeah, just this way the example. Okay, this is the example. Now, here you can see the statement, print statement. So it gives us the output like this loaded 1000 10,015 labeled images from metadata. Yes. So all 10,015 rows in the metadata successfully mapped to a class and none fell through as unmapped, confirming our seven code dictionary covers every diagnosis code actually present in this data set. So the class balance is heavily skewed, that is 8,061 banning, that is 80.5% versus only 1,954 malignant, that is 19.5%, noticeably more imbalanced than the blood cancer data sets. Yeah. So keep this number in mind. It directly explains a problem we'll see later in training. Okay, so let's get back. Locating the actual image files. Here we can see the code. Yes. It loops through both capitalized image folders and listing every file inside. Okay. So here you can see fname. Yes. Fname dot lower dot ends with dot jpg dot jpg dot png filters to only actual image files. That is, it is case sensitive. So dot jpg would also match. It is case insensitive. So if it is written in caps dot jpg, then it would also match. Okay. It is not case sensitive. It is case insensitive, right? And here you can see os.path split text. It strips the file extension, turning ISIC into .jpg into ISIC 0027 format, which is exactly the image ID format used in the metadata CS, letting us match the two together. For that, you can see the output here, that is found 10,015 image files on disk. Okay, now let's move further for now here we'll be keeping the class ratio same, splitting the data. Okay. The logic is, of course, identical to the blood cancer as we have seen before. Yeah. Here, this line of code, this much, groups image IDs by class, that is only keeping one once we actually found a file for, and so the 15% validation split can be taken independently per class, preserving the same benign or malignant ratio in both train and well, exactly like we did for our blood cancer before. Okay, so here output is this. You can see it checks the ratios, that is uh, train to banning is 6852 images. That is approximately uh, you can say 80.5% of banning. And yes, so these are the ratios you can see. Now let's move further. So here we have set our image size 160 to 116 to 160. That is bigger than your blood cancer's image size. Uh, because this is the size for mobile net V2 that was originally designed and pre-trained around. So matching it lets the pre-trained weights transfer more effectively. Yes. So here also we have used this synthetic demo equals to false as we have loaded the real data set from Kaggle. You can see that. Now let's move further. That is loading and pre-processing images. Yeah, so here is our loading and pre-processing of images. So here you can notice here the augmentation pipeline has one more transformation than blood cancers. That is random contrast zero point 0.1. This matches exactly what your skin cancer detection models slide said. That is like skin appears differently across skin tones and lighting conditions. So contrast jittering helps the model generalize across that variation, and something less critical for blood smear microscopy images, which are captured under much more standardized lab conditions. And yes, you can also notice there is no separate rescaling, 1 upon 255, that layer here, unlike blood cancer. That's because mobile NetV2 has its own specific reprocessing requirements and handled differently in the next block. Okay. So here's the output. You can see that it matches exactly the train well totals from above block. Yes. And a good consistency check, confirming nothing was lost or duplicated between reorganizing and loading. Okay. Now let's move further. That is to build the model with the help of MobileNet V2 transfer learning. Yes, here MobileNet V2 loads a CNN architecture that was already trained on ImageNet 1.4 million general photos and 1,000 categories like cats, cars, furniture, and etc. And here you can see include top equals to false. It means that it discards MobileNet V2's original final classification layers, which were built for 1,000 unrelated categories and keeping only the feature extracting backbone. Then here you can see weights equals to ImageNet. It actually downloads those pre-trained weights, and this is the step that needs internet confirmed working below. Then here is the base model dot trainable equals to false. Uh, freezes every one of those pre-trained weights, so they won't change during stage one training. And we are only going to train a small new classifier on top of them initially. Okay. So now you can see here inputs. So here You can see pre-processed inputs. Here, mobile net V2 expects pixel values scaled to a specific range that is roughly from -1 to 1 rather than the simple 0 to 1 scaling we used for blood cancer. This function applies exactly the transformation MobileNet V2 was originally trained with. Now here you can see x equals to base model, x comma training equals to false. It passes the pre-processed image through the frozen pre-trained backbone. Training equals to false, where specifically ensures internal details like batch normalization behave in inference mode even during our own training loop, and which is important for correctly using a frozen pre-trained model. Yes, here we have used global average cooling and dropout is zero point 0.3, and the final dense 1 comma sigmoid, our output layer work identically to the blood cancer model's final stages. Okay, so yes, now move further. It is the same compile setup as we seen previously. Uh, Now in output you can see this confirms the exact moment MobileNet V2's pre-trained waves, and yes, were downloaded from Google servers. Here, true divide and subtract are the internal operations that make a pre-processed input. Here, Keras automatically names these as individual layers when it traces through the function, even though we wrote it as one line of code. Yes. So now let's move further. That is our stage one, that is training. Here, these callbacks are just identical to what we have seen in the blood cancer. Okay. And here also it stops early validation. AUC hasn't improved in 4 epochs. So here number of epochs are 12. Here you can see only 9 epochs have run, not all 12. You can notice it. Yes. Now here you can see 267 batches per epoch. Yes. That how we got 267, that is 8,501 513 divided by 32, that is approximately equal to 267. Why we have divided it by 32? Because batch size is 32. So you can see the at the accuracy in starting it is 0.8009, then 0.8257, then 0.8381, 0.8359, 0.8417, 0.8433, 0.8481, 0.8453, 0.8467. That is okay. Now let's see recall alongside. It is 0.2812, 0.3805, 0.4118, 0.4148, 0.4305, 0.4329, 0.4449, 0.4485 and 0.4618. Yes. So now you can see in first epoch, accuracy is already respectable, like it's around 80%, but recall is only 28%. This is exactly the class imbalance trap explained on our model evaluation matrix slide. Yes, because 80.5% of the data set is Benning, a model that leans toward guessing Benning most of the time will rack up high accuracy almost automatically. Yes, while still missing the majority of actual malignant cases. This is genuine, unfiltered example of that exit failure mode happening live, not a hypothetical. So by Epoch 9, recall did improve to 46.18%. That is a real progress, but still catching under half of true malignant cases. Yes, so hence only 9 epochs of the requested 12 appear. This means early stopping triggered. Having detected no improvement in validation AUC for 4 consecutive epochs. You can see that. Yes, 0.8582, 0.8565, 0.8517, 0.853. It's continuously dropping. Okay, now let's move further to the stage 2, that is fine tune. Here, base model.trainable equals to true unfreezes the entire backbone, but then the loop immediately refreezes everything except the last 30 layers. Yes? So here layers colon 30 means all layers except the last 30, setting exactly those to non-trainable. This is the standard fine-tuning compromise. Let the deepest, most task-specific layers adjust slightly to the skin lesion imagery while keeping the earlier, more general layers, that is edge or texture detectors, untouched. Now recompiling with a dramatically lower learning rate, that is 1e minus 5 versus the earlier 1e minus 3. This is 100x smaller and is essential here. We are nudging pre-trained weights gently, not overriding them with large updates that could destroy the useful knowledge already encoded in them. So here's the output you can see. Yes, here we have number of epochs set to 6. Okay, so all 6 epochs have run. Now here you may notice in epoch 1 actually looks worse than where stage 1 left. Yes, AUC dropped from 0.607 to 0.806. Yes, 0.806. And yes, loss jumped from 0.3465 to 0.4033. 0.4033. 0.445. 0.3465. Yes. This is expected and completely normal. The moment you unfreeze previously frozen layers, the model temporarily forgets some of its calibration as those weights start shifting again. By the final epoch 6, it recovers and surpasses stage 1's best, that is, AUC reaches 0.8760 and recall improves further to 50.39%. Now let's plot some the training curve combined. Yes. Since the training has happened in two separate dot fed calls, that is stage 1 and stage 2, each produce its own separate history, the object. This concatenates both stages, metric lists end to end using Python's this plus on lists, which joins them, yes, into one continuous timeline for plotting. Here you can see I have used dot axv line. It draws a vertical dashed line at x position. You can see over here. Since stage 1 ran for 9 epochs, confirmed by early stop, this draws the marker exactly at epoch 9, visually separating stage 1 from stage 2 on the combined chart. Yes, now let's see the two charts. The lost one is on the left, and on the right, there is the ROC AUC code. So here, the blue line is the training line. It descends steadily, you can see, and it hits the dashed line, that is fine tune starts line around epoch 9, and then we can see that it's a spike over here. Yes, right at the boundary from about 0 point, you can see it would be 345 something to roughly 0.40. This is the temporary forgetting moment from unfreezing layers visible directly in the chart. So then resumes descending down to above 0.33 by the final epoch. Now let's come to ROC AUC. It is just the mirror image, you can say, of the same pattern. Yes, climbing from about 0.755 up to up towards to 0.86 and then dipping down to about 0.807 and right at the fine tuned boundary, then climbing again to finish around, you can see 0.876 to 0.88 for both train and validation state. Yes, which end up converging closely together. That is a reassuring sign that the model isn't wildly overfitting. Now let's move further. That is final evaluation and save stage. Here batches, 47 batches, since the data set was divided by 32. That is 1502 was divided by 32. So it was almost 47 batches. And this is the single most important number to highlight. Yes. Now final validation accuracy is respectable here. That is 85.02%, and the AUC is solid, that is 0.8754, and both the numbers that look good at a glance, but final recall is only, you can see, 36.86%, meaning this model correctly catches barely more than 1 in 3 actual malignant lesions in the validation set. Yes, so that's a serious real limitation, and it's a direct live consequence of the 80.5% to 19.5% class imbalance we saw all the way back. Yes, yes. So now let's get back to our slide. So now let's start with part 5, that is evaluation and explainability. It is the most important part for real world trust. That is evaluation and explainability. Building a model is one thing, but providing it's reliable and being able to explain its reasoning to a doctor is what actually makes it usable in the real world. Yes. We have built several models by now, but how do we know if a model is good or not? The most obvious metric is accuracy, that is, percentage of predictions the model got right. But there's the trap. In a data set where 95% of patients are healthy and only 5% have cancer, a lazy model that always predicts healthy would score 95% accuracy while being medically useless. This is why we use more nuanced metrics, that is, precision tells you of all patients flagged as cancers and how many actually were. Recall or sensitivity tells you of all patients who actually have cancer, how many did the model correctly catch, and F1 score balances the two. Uh, that is, in cancer diagnosis, we usually care more about recall than precision because a false negative, that is, telling a cancer patient they are healthy, is a far more dangerous than a false positive. Yes? For example, imagine airport security. If they let a genuine threat through a false negative, that is catastrophic, and if they extract and if they extra screen an innocent traveler, that is a false positive, that's just an inconvenience. Cancer screening has that exact same is asymmetry, which is why recall matters so much. The confusion matrix is the simple table that allows those matrices are actually calculated from. It has four cells. Yes, a true positive is when the model correctly predicts cancer and the patient has cancer. A true negative is when the model correctly predicts healthy and the patient is healthy. Then the two error types, that is a false positive, is when the model predicts cancer but the patient is actually healthy, and an unnecessary scare. A false negative is when the model predicts healthy but the patient actually has cancer. That is the most dangerous error in medical diagnosis, since a real case slips through undetected. When you look at confusion matrix, the first thing to check is that bottom column. How many false negatives? Because minimizing that is often the whole point of building the model. Let's have a look for confusion matrix. So this is your confusion matrix. Here are the predicted outcomes, and here are the actual outcomes. This is true positive, false negative, false positive, true negative. This is how your confusion matrix looks like. Okay. And here are the definitions for each of the following and their formulas too. You can see it. Yeah. And here's also an example for it for a dog image recognition. So you can come to Gigs for Gigs and just have a look for it. Now gets back to our slide. Now, a classification model doesn't just output malignant or benign directly. It usually outputs a probability like 87% chance of malignant. And we choose a threshold, commonly 50%, above which we call it malignant. The ROC curve helps us understand the trade off involved as we slide that threshold from 0 to 1, plotting the true positive rate against the false positive rate. AUC, the area under that curve, compresses this trade off into a single number. That is, an AUC of 1.0 means perfect separation, and zero point 0.5 means no better than random guess. This let us compare models fairly, and it remains reliable even when the dataset is imbalanced, unlike plain accuracy. So let's have an example. Now, let's say it's like judging a metal detector by testing it across every possible sensitivity, setting it from barely sensitive to hypersensitive and asking across that whole range, how good is it overall at telling metal from non-metal? That overall summary is what AUC captures. Yes, cross validation. What if we just got lucky or unlucky with how we split our data into training and testing sets? A single split might by chance put unusually easy or hard cases into the test set. Yes, there is a possibility of it, giving a misleading sense of how good our model really is. Cross validation solves this by testing more thoroughly. In k-fold cross-validation, we split the data into, say, five or equal folds and train the model five separate times, each time using four folds for training and holding out a different fold for testing. We average the five scores together, giving a much more trustworthy estimate of real-world performance. This matters especially in medical ML where datasets are often small and so results can be sensitive to exactly how the data gets split. Yes, it's like judging a student's understanding by giving them five different practice sets instead of just one. That is, if they consistently score well across all five, you trust that far more than if you would only see one test where they happen to get lucky questions, right? As our model gets more powerful, especially deep learning and boosted trees, that is, they also tend to become harder to interpret. We call this black box models. That is, you see what goes in and what comes out, but the internal reasoning is opaque, even to the people who built it. In healthcare, that's a serious problem. If a model tells a doctor this patient has cancer but can't explain why, that doctor has no real way to sanity check the prediction before acting on it. This is where explainable AI or XAI comes in, that is, techniques designed to make model decisions understandable to humans beyond trust. XAI matters for regulatory approval of medical AI tools, and it helps developers catch cases where a model relies on spurious or biased patterns rather than genuine medical signal. Yes? Imagine a brilliant but silent diagnostician who is always right but never explains their reasonings. That is, would you feel comfortable acting on their diagnosis without a second opinion? XAI turns that silent genius into someone who can actually show their work. Yes? SHAP and LIME are the two most widely used tools for actually implementing explainability. SHAP, that is Shapely Adaptive Explanations, borrows an idea from game theory to assign each features a contribution score for a specific prediction. That is, how much did this feature push the prediction toward malignant or away from it? Line, that is local interpretable model agnostic explanations, approximates the complex model's behavior locally around one specific prediction using a much simpler interpretable model just to explain that case. Both are model agnostic, that is, they work regardless of underlying model type in our uh, yes. Let's understand this with an example. Say, like, if a model says this patient is 92% likely malignant, SHAP is what lets you ask, okay, but why? Which specific measurements drove that number? And get a real itemized answer, like the irregular cell order contributed plus 15%, while the smooth texture contributed 3%. Yes? Now, we close with part 6, that is applications and future. Here we connect everything back to the real world, that is how these models are actually used clinically today. An honest look at their current limitations and where this field is headed next. So, let's zoom out and talk about where all of this gets used in the real world. The most important framing, ML in healthcare, is a second opinion tool, not a replacement for doctors. It flags high risk cases for a radiologist, pathologist, or oncologist to review more closely, helping prioritize their limited time. Concrete applications like automated triage of mammograms, pre screening scans, and flagging the ones most likely to need urgent treatment, such as leukemia detection assistance from blood smear images, speeding up lab diagnostics, and mole or lesion risk scoring built into dermatology apps, sometimes directly on patients' phones. This last category, that is mobile and telemedicine apps, is especially impactful in undeserved or remote areas where access to a specialist might otherwise mean weeks of waiting. Think of it like a hospital's emergency triage. Mm. But for imaging data quickly, sorting cases into needs, urgent attention versus can wait so the limited number of specialists spend their time where it matters most. Now, it's important to be honest about where this technology still falls short. First, data limitations. Many cancer subtypes are rare, meaning there isn't enough labeled data to train a reliable model. Second, privacy. Medical records are among the most sensitive data that exists, and regulations rightfully make it hard to freely share patient data between institutions, that is slowing the collaborative research. Third, bias. Yes. If a model is trained mostly on data from one demographic, that it can perform significantly worse on patients outside that group. Serious fairness and safety concern in a field as a high stakes as cancer diagnosis. And finally, even a technically excellent model faces a long road to clinical use. That is, regulatory approval, clinical validation trials, and integration into hospital workflows all take significant time. It's a bit like a translator who is only ever studied one regional dialect and they sound fluent and confident but make consistent, invisible mistakes outside the dialect they actually learn. A biased model can be just as confident wrong. So here where is this field heading? Multimodal models combining imaging, genomic, and clinical history data together rather than just one data type in isolation. That is expected to produce more personalized and accurate risk predictions. Since real diagnosis rarely relies on just one type of evidence, federated learning is another exciting development. It lets multiple hospitals collaboratively train a shared model without sending raw patient data outside their own pods. That is, only the learned model updates get shared, addressing a lot of the privacy concerns we just discussed. We are also likely to see deeper integration of ML into real time clinical workflows and even wearable devices, enabling continuous risk monitoring. And as explainable AI techniques mature, we should expect faster clinical trust and adoption. Let's move further. So let's bring this all together. We started with the basics, that is, what cancer actually is and why catching it early makes such a dramatic difference in our outcomes. And we built up a toolkit of machine learning algorithms from simple and interpretable ones like logistic regression to powerful but more opaque like deep learning models. And the right choice depends on your data type and how much interpretability you need. We saw how these techniques apply specifically across blood, breast, and skin cancer, each with its own data sources and modeling approaches. And critically, we covered how to properly evaluate these models using confusion metrics and ROC, AUC, and cross validation, and how to make them explainable using tools like SHAP. Because in medicine, a prediction model without justification isn't good enough. So, if there's one takeaway I want you to live with, it's this that machine learning is not here to replace doctors, but yes, it's here to give them faster, more consistent, and more transparent tools. So, human expertise and data driven insight together can catch cancer earlier and save more lives. Yes? So, let's move further. So, that brings us to the end of this session. So, thank you so much for continuously supporting me. So now, if you have any queries, so you can reach out to us at biotechrebioin@gmail.com. Thank you.